Hi everybody. In our last lecture, we had completed up to the 35 number question. This was the question, 35 number question, and it was about the dipole antenna. Okay, so let's start from 36 number question. Okay, so the 36 number question has asked to find the assumption for deriving the expression for electric field and magnetic field due to an oscillating magnetic dipole. Okay, where this B is the radius of the circular loop in which the current is flowing, and this is R is the position of the observer. Okay, that means at the coordinate at which the observer is observing the system. Okay, so if you see this question is a theoretical based question. That means it is better to remember the question's answer so that it will be helpful in the competitive exam. That is, this answer is option D. That is, the size of the dipole is small compared to the wavelength of the radiated. That means uh, the size of the dipole, that is the length q minus q. Okay, between that length should be smaller than the wavelength. Okay, this is the answer. And if you want to know this concept better in a better way, so please refer to the DJ Griffith Electrodynamics book. Okay, so in that part, in the radiation part, it is fantabulously explained and derived all the parameters, and it has taken all the assumptions. This is one kind of assumption. This is a kind of assumption, that is the the wavelength of the radiated radiation should be greater than the dipole size. This is a condition. There are also different kind of condition for this same case. Okay, so let's come to the 37 number question. The 37 number question has asked to find the power factor of a RLC circuit. What is RLC circuit? In series. That means a series, and it is in AC source. That means a alternating current is connected to the this circuit element. The circuit element is a a resistance, a inductor, a capacitor. Okay, so to and if you want to find the solution of this 37 hour question, we know that this power factor is cos phi. Okay, what is this cos phi? Where this phi is tan inverse omega L minus 1 by omega c by r. Okay, and this omega L and 1 by omega c are the uh, inductive reactance and capacitive reactance respectively. Okay, so as the question is asked about at the time of resonance, that means at resonance this omega L and omega 1 by omega c both will be equal. That means XL should be XC. These are the inductive reactance, this is the capacitive reactance, XC. Okay, so when this both term will be equal, that means this the numerator here, tan inverse, this numerator, that will be 0. So 0 by r, so 0 by something is also 0. So tan inverse 0 is 0. This is tan inverse 0. So when phi is 0, because tan inverse that quantity was phi, so phi equal to 0. So when phi equal to 0, cos phi equal to 1. Okay, that means here option B is the correct one. Now coming to the 38 number question, the question has asked to find the angular frequency in a LC circuit. Okay, it is connected to a AC source where this inductance is 80 millihenry and capacitance is 8 microfarad. So we know that for a LC circuit, the capacitive reactance, when you make this equal with the capacity reaction with the inductive reactance, you'll get this omega equal to root over of LC, 1 by root over of LC. So if you put the value, whatever data are given, if you put those value here, you will get 1250 hertz. Okay, so So option C is the correct one. Now coming to the 39 number question. The 39 number question has asked to ask. It has given a criteria, that is the a case that the RLC circuit is in underdamped condition, and it is connected to a DC source, and it is given some case like the angular frequency omega 1, that is the oscillatory current frequency. Okay, it is half of the intrinsic angular frequency omega naught. What is this intrinsic angular frequency omega naught? This is the angular frequency arises due to the inductance and capacitance. Okay. Now, if you see the solution at underdamped condition, this omega 1, that is, what is this omega 1? Oscillatory current angular frequency. This omega 1 is equal to root over of omega naught square minus k square, where this k square, you can see the k is this, where 2k is r by l. So when 2k is r by l, k will be r by 2l. So k square will be r square by 4l square. Okay, so this is the condition. This is the formula to apply. Okay, so omega, this is the given condition. Omega equal to omega naught by 2. So if you put here, if you put those value here, okay, you will get omega naught by 2 equal to this, and if after solving, you will get r equal to 3l by c. Okay, this is the correct one. So if you see if you see the options, option D is the correct one. Okay, now coming to the 40 number question. 40 number question has asked, it has given a LC circuit, and the data are given as that it is given that the current builds up to 2 by 3 of the steady state value in 4 seconds. Okay, let me read it once again. The current in LC circuit builds up to 2 by 3 of the steady state value in 4 seconds. The inductive time constant. Oh, it is asked to find the inductive time constant. Okay, so if you see the solution, this is the solution. Okay, so if you see this, yes, the growth in current, that is the I, is equal to I naught by 1 minus e to the power minus t by tau l, where this tau l is the inductive time constant. Okay, and I naught is v by r. Okay, this I naught. So if you see the solution, this will be 2 by 3 if you put the value, because it has given the condition that this I is this I, this I is this I is equal to 2 by 3 of the I naught. Okay, so if you put in those value, you will get, and after solving this, you see those solutions, how it is proceeding. You will get ZL equal to 4 by ln c ln 3.